Hello, my dear students. I once again welcome you all to this current lecture. As you know that in the last lecture, we studied one important point regarding the structure and the shape of the molecules, that is called as the aromaticity. In that, we studied one important rule that is called as the Haeckel's rule for aromaticity. So, how that Haeckel's rule is useful for determining or for assigning the nature of a particular organic molecule, so that we studied in a last lecture. Now in a current lecture we are going to take some important concepts regarding the covalent bond present between the atoms in a particular organic molecules. So what are the different properties of that particular covalent bond, so that we have to study. So the first important property of a particular bond present between the atoms is called as the bond length. What is meant by the bond length of a particular molecule, so that we have to study. So if we consider a general example of a molecule, suppose AB is a molecule, A single bond B. So whenever these two atoms in a molecule get joined by a particular chemical bond, suppose a covalent bond is present between this atom A and B, whenever we say a bond length of molecule AB, then what is the meaning of this particular bond length, that we have to study. So this bond length is nothing but, it is defined as, the bond length is the mean distance, it is the mean distance, it is the mean distance between the nuclei, it is the mean distance between the nuclei of bonded atom mean distance between the nuclei of bonded atom is called as bond length, is called as bond length, bond length, or it may be called as the bond distance, it may be called as the bond distance. So whenever we use the word bond length or bond distance, so it means that it is nothing but the mean distance between the nuclei of the bonded atom. So if we consider this AB molecule, then what is the mean distance between the nuclei of this atom A and nuclei of this atom B, then that is called as the bond length or bond distance of the AB molecule. This bond distance or bond length is expressed in a unit of Armstrong unit. This Armstrong unit is the unit for this bond length. 1 Armstrong unit. This Armstrong unit is represented by the sign A0. So 1 Armstrong unit is equal to 10 raised to minus 8 centimeter. So this unit for this bond length is an Armstrong unit. 1 Armstrong unit is equal to 10 raised to power minus 8 centimeter. Now whenever a molecule get formed by the suitable chemical bond, then what happens? These atoms are collected together with the help of this particular chemical bond. So we can say that this bond length is very much important as far as the constituent atoms of a molecule is considered. Now, depending upon the nature of the atoms present in a molecule, the value or the magnitude of this bond length get changed. Suppose if we consider the different types of the bonds, suppose if you consider the different types of the bonds and their respective bond length, then it get vary depending upon the nature of the atoms present in a molecule. Suppose if we consider the first bond between carbon and chlorine atom, second between the carbon and the bromine atom, and the third between carbon to that of the iodine atom. Now, as far as the atoms present in a molecule is considered, it is or it affects the magnitude of the bond length. So, for example, if we consider these particular bonds, the carbon atom is a common, but we change the second atom, that is a halogen atoms. We are going from chlorine to the iodine. Now we know very well that as we go from chlorine atom to the iodine atom, the atomic size of these halogens going on increasing. As this size going on increasing, it affects the magnitude of the bond length, as the value of the bond length for this CCl bond is 1.76 Armstrong unit. The same value for the second bond, that is a carbon single bond bromine, is equal to 1.94 Armstrong unit. And why this is a difference? Because we know that as compared to chlorine, the atomic radius of this bromine is a more, and that's why its bond length is a more for this carbon single bond bromine. Same case is there for this carbon single bond iodine bond also. Its bond length again going on increasing, that is equal to 2.14 Armstrong unit. So from these three different bond length magnitudes, we can say that as the atomic radius of an atom going on increasing, it affects the magnitude of the bond length. Now, the same value of this bond length, we may consider it in a different type of the bonds with different hybridization. Suppose if we consider the bond, if we consider the different types of the bonds, their hybridization, then percentage of S character, we consider here percentage of S character, and finally we have to consider their bond length. So these four different parameters are correlated with each other. So first of all, if we consider carbon single bond carbon, secondly if we consider carbon double bond carbon, and third we consider carbon triple bond carbon. So we have to take the three different types of the bonds that is present in alkane, alkenes and alkynes. We know very well their respective hybridization. So whenever a carbon single bond carbon is there, its hybridization is sp3. When it is a carbon double bond carbon, it is sp2 hybridize, and when it is a carbon triple bond carbon, it is a sp hybridize. We know the respective percentage of S character. It has the 25% of S character, it has the 33% of S character, and it has the 50% of S character. Now we have to correlate how this bond length is depends upon the hybridization as well as the percentage of S character. Now we know very well that as the percentage of S character going on increasing, then we can say that the atomic size or the atomic radii of a particular atom going on decreasing, because the percentage of S character as increases, the atomic size going on decreasing. So it affects the magnitude of the bond length. So if we consider the first value of bond length for this carbon single bond carbon, it is equal to 1.54 Armstrong unit. Now, if we go toward the second type of bond, that is a carbon double bond carbon, the percentage of S character going on increasing, and it affects the magnitude of bond length. It becomes equal to 1.34 Armstrong unit. So this bond length going on decreasing as the percentage of S character increases, and the same situation is there for this third bond, carbon triple bond carbon. The percentage of S character is a 50%. So the bond length is a least in case of the carbon triple bond carbon chemical bond. So from this data we can say that this bond length depends upon the type of the hybridization as well as the percentage of S character. It is very important as far as the magnitude of this particular bond length is considered. So from this we can say that this bond length is a very important property of a particular chemical bond. It gives us an idea regarding the strength of a chemical bond in terms of its magnitude. If or if the bond length is more, then what happens? Its bond strength is a less and vice versa. So if we compare these three type of the bonds, single bond, double bond and triple bond, in this case what happens? The bond length of carbon, single bond carbon is a more. So we can say that its bond strength is a least. So bond length and bond strength are inversely proportional to each other. So this is the first important property of a chemical bond called as the bond length. Now the second important property of a chemical bond is called as the bond angle. The second important property of a chemical bond is called as the bond angle. Now what is meant by bond angle? So for this purpose, if we take a simple example of molecule, that is, we take here methyl chloride. We take here suppose the example of suppose if we take example of methyl chloride, this is a hydrogen, second hydrogen, third hydrogen, and this is a chlorine atom. So this is called as the methyl chloride molecule. Now if we take this methyl chloride, so from this methyl chloride, if we want to define this particular bond angle, now what is the bond angle? So this bond angle is defined as the angle between, it is the angle between, it is the angle between adjacent two bonds, adjacent two bonds on an atom is called as bond angle. It's called as bond angle. So if we consider this molecule methyl chloride, if we want to consider the bond angle between the two bonds between this carbon and hydrogen to that of the bond between carbon and chlorine, so this angle between these two bonds on an atom, this atom is a common, there is a carbon on this atom, two types of the bonds is there on either side. First is a carbon single bond hydrogen, second is called as a carbon single bond Cl. So this angle between these two bonds is called as the bond angle. So its value is equal to 108 degree. So same case is there. If we consider another type of body bond on this carbon, first is the carbon single bond hydrogen and second is again carbon single bond hydrogen. So this bond angle is found to be 110 degree. So this is a simple property called as a bond angle, that is nothing but the angle between the adjacent two bonds on an atom. So in this methyl chloride, these two types of the bond angle is there. Now this bond angle is again depends upon the structure of a molecule, whether it is a symmetrical structure or unsymmetrical structure, what is the hybridization of the given molecule. On that also the magnitude of this particular bond is dependent. So if we consider suppose the type of the hybridization, if we consider here suppose the type of the hybridization, next is its respective bond angle value. How this hybridization is important? So if we consider the three basic types of the hybridization, sp3, second is sp2, next is your sp. So if we consider these three different hybridization, then it has the different value of the bond angle. For the first tetrahedral geometry or the hybridization, its bond angle value is a 109.5 is a 109.5 Armstrong unit. For the sp2 hybridization, its bond angle is equal to 120 degree. Its angle is a 120 degree, and for this sp, its bond angle is equal to 180 degree. So we can say that this bond angle is maximum in the case of carbon triple bond carbon compound, that is a compound having sp hybridization. So in this way we can say that this bond angle value depends upon the hybridization involved in a particular chemical bond. Now if we take into consideration the different type of the examples of the molecules, then the structure also affects the magnitude of the bond angle. Suppose if we consider the two different type of the organic molecules, first of all, if we consider here a water molecule, O single bond H, again single bond H. So this is a water molecule. We know very well that this water, in a water molecule, oxygen has the two non-bonding electron pair. This is the first non-bonding electron pair. At the same time, it has the second non-bonding electron pair. So two non-bonding electron is present on this oxygen atom. And the second example we consider here, that is a ammonia. In this ammonia, the 3 sigma bonds is present between nitrogen and hydrogen, and one non-bonding electron pair is present on this nitrogen. Now, if we want to study the magnitude of the particular bond present between these atoms in these two different molecules, for this purpose, we have to take into consideration how many non-bonding electrons are present on this centrally situated atom. So, in this case, two non-bonding electron pair is present first, and this is the second, while in this compound only one non-bonding electron is present on a nitrogen, due to which what happens, the bond angle value is different in both these cases. In the first case of water molecule, bond angle is a 104.5 degree. It has the bond angle of 104.5 degree, while in the second case, between these two adjacent bonds on this nitrogen atom, the bond angle value is equal to 107.1 degree. So this is the difference between the bond angle in these two molecules. And why this is so? It depends upon the number of non-bonding electron pairs present on a centrally situated atom. In this case, we have to take into consideration the non-bonding electron pair repulsion. So that also affects the magnitude of the bond length. Okay, so this is a second important property of a bond called as the bond angle. Now, the last important property for the bond of a particular molecule is called as the bond energy. The third important property of a bond is called as the bond energy. Bond energy. So, bond energy of a particular bond is nothing but whenever we consider a particular bond, suppose if I consider here a simple bond between this hydrogen, single bond hydrogen in a H2 molecule. So what is my bond energy? So bond energy is nothing but energy. It is the energy required to break a bond, energy required to break a bond into its constituent radicals, then it is called as the is called as bond dissociation energy. Bond dissociation energy. So this is a important property of a particular bond called as the bond energy. So whenever we consider a particular bond between the two atoms, whenever we break this bond into its constituent radicals, H radical and the second H radical, then what is the amount of energy which is required? So that energy is called as the bond dissociation energy. It is expressed in a unit of delta H. So for this hydrogen molecule, this bond dissociation energy is equal to 104 kilocalorie per mole. Kilocalorie per mole. So this is a very important property as far as the strength of a bond is considered. So this is the energy which is required to break a bond into its constituent radicals. So this is one of the possible definition of the bond dissociation energy. In another way, this bond dissociation energy may be defined as the amount of energy this amount of energy liberated when a bond is a bond is formed or broken, a bond is formed or broken, formed or broken, it's called as bond dissociation energy. It's called as bond dissociation energy. So these are the two different type of the definitions for a particular bond dissociation energy. First of all, bond energy is defined as the energy required to break a bond into its constituent radicals is called as the bond dissociation energy, or the amount of energy liberated when a bond is formed or broken is also called as the bond dissociation energy. Now, the two important concepts is there. One is a bond energy, bond energy, and second is a bond dissociation energy, bond dissociation energy. So what is the difference between these two energies? So whenever this bond energy is considered, this energy is expressed the bond, the breaking of bond or formation of bond present between the two atoms. Whenever we consider an individual bond between the two atoms, then that is nothing but the bond energy. But whenever we consider a molecule which has the different type of the chemical bonds, for example, if you consider this type of the molecule, this molecule has the four different type of the sigma bonds: bond between carbon and A, bond between the carbon and atom B, bond between the carbon and atom D, and bond between carbon atom E. So whenever these four type of the bonds is there, when we take a average of, when we take a average of all the bond energy, it is get it get this, whenever we consider this energy required to break an individual bond, it is a bond dissociation energy. It is the bond dissociation energy. And whenever we consider the individual bond, the energy required to form or break a bond, it's called as the bond dissociation energy. But whenever we consider a molecule in which more than one chemical bond is present, at that time, if we take an average of the bond dissociation energy of all the bonds, the first bond, second bond, this is the third bond, and this is the fourth bond. So if we take a summation of all these bond dissociation energy, then that energy is called as the bond energy of the particular molecule. So this is the two different ways to express the energy of a molecule. When only one type of the bond is there, then that energy for that particular single individual bond is called as the bond dissociation energy. But whenever a molecule is there having more than one chemical bond, at that time what happens? If you take an average of the energy, bond dissociation energy of all the bonds, if we take that particular average, then that is called as the bond energy of a particular molecule. So in our current lecture, we studied the three important properties of particular chemical bond. First is called as the bond length, second is called as the bond angle, and just we completed the third important property of a bond, that is called as a particular bond energy or bond dissociation energy. So this is very important properties as far as a particular chemical bond is considered. So with this I stop here. Remaining points we will take in a next lecture. Thank you so much.